Welcome to GATE class. So today we are going to start with the correlation theorem. So according to this theorem, if G1t has Fourier transform G1f and G2t has Fourier transform G2f, and also we are assuming that G1 and G2 are complex valued. So assuming that G1t and G2t are complex valued signal, assuming that G1t and G2t are complex valued signal, then minus infinity to plus infinity G1t G2 conjugate t minus tau dt, if we find out the Fourier transform, then it is equals to G1f G2 conjugate f. So it is from minus infinity to plus infinity G1t G2 conjugate t minus tau dt has the Fourier transform G1f and G2f. So what is G2 conjugate f? So G2 conjugate f is the complex conjugate of GF, is the complex and tau is the time variable, and tau is the time variable involved in defining the inverse Fourier transform, in defining the inverse Fourier transform of product of G2f conjugate. So next is our Rayleigh energy theorem. So according to this theorem, if GT has Fourier transform GF, then we can write it as modulus minus infinity to plus infinity modulus of GT square dt, and it is equals to minus infinity to plus infinity modulus of GF square dF. So both the signals will give the energy. Of that signal GT. So we can find out energy by applying this formula either, or also we can apply this formula for getting the energy. So this is called the Rayleigh energy theorem. Next is differentiation in the frequency domain. Differentiation in the frequency domain. So according to this theorem, if we have minus jt into xt, then the Fourier transform is equal to dx omega divided by d omega, and omega is the angular frequency. So let us find out some problems, find out the Fourier transform of some basic problems like xt is equal to cos omega naught t. So let us find out Fourier transform xf. So let us solve this. So xt is written as e raised to the power j omega naught t plus e raised to the power minus j omega naught t divided by 2, and also better to write in the f. So it is 2 pi f naught t plus e raised to the power minus j 2 pi f naught t divided by 2. Now that Fourier transform of this is Fourier transform of e raised to the power j 2 pi f naught t divided by 2 plus e raised to the power minus j 2 pi f naught t divided by 2. So the Fourier transform is equals to xf is equals to 1 by 2 Fourier transform of e raised to the power j 2 pi f naught t plus 1 by 2 Fourier transform of e raised to the power minus j 2 pi f naught t, and xf is equals to 1 divided by 2 del f minus f naught plus 1 by 2 del f plus f naught. So we can draw that this is xf and here we have f, then we have f naught, here we have minus f naught. So we have a delta function present at f naught and another delta function present at minus f naught. So we have this delta function. So we have two delta function present. One delta function is present at f naught and another delta function is present at minus f naught. So this is the Fourier transform of cos omega naught t. Let us find out the Fourier transform of sin omega naught t. So xt is sin omega naught t, that is we can write it as sin 2 pi f naught t. So f naught is 1 divided by t naught and t naught is time period. So find xf. So again, for this type of problem we can write it in this exponential form. So xt is equals to 1 divided by 2j e raised to the power j 2 pi f naught t minus e raised to the power minus j 2 pi f naught t. Now we can write it as 1 divided by 2j e raised to the power j 2 pi f naught t minus 1 divided by 2j e raised to the power minus j 2 pi f naught t. This is xt. So the Fourier transform of xt is equals to Fourier transform of 1 divided by 2j e raised to the power j 2 pi f naught t minus Fourier transform of 1 divided by 2j e raised to the power minus j 2 pi f naught t. That is nothing but we have del f minus f naught minus 1 divided by j2 del f plus f naught. So the Fourier transform is finally we can write it as xf is equals to 1 divided by 2j del f minus f naught minus del f plus f naught. So this is the Fourier transform of sin omega naught t. Let us find out the very important transform, that is let us find out the Fourier transform of signum. Let us find out the Fourier transform of signum t. So how to find out the Fourier transform of signum t? So the question is find out the Fourier transform of signum t. Signum t is equals to, the function signum t is defined as 1 when we have t greater than or equal t greater than 0 or equal to 0, and it is minus 1 when we have t less than 0. So the graph is like this. This is signum t. Here we have plus 1, when we have t greater than 0 and minus 1 when t less than 0. So this is the graph of signum t. So let us find out the Fourier transform of signum t. So signum t is basically that if we just go for that Dirichlet conditions, then the first condition is avoiding. The Dirichlet condition is that it should be integrable. So this signum function is basically not following the very first condition of the Dirichlet's condition. So what we can do, we can find out the Fourier transform of signum t, let xt is equals to signum t, and we are going to find out the Fourier transform by assuming some basically some approximation we are going to assume. So it is the limit, if we take this assumption that limit a tends to 0, e raised to the power minus a modulus of t signum t. So let us assume this xt. So xt is equals to signum t. So this is also equals to this term, because when a tends to 0, this term will become 1. So when basically when limit a tends to 0, e raised to the power minus a modulus t will become nearly equals to 1. So it will become nearly equals to 1. So it means that since it is 1 multiplied by signum t, so that is equals to signum t only. And what is modulus of t? So modulus of t is equals to 1 when we have t greater than or equal to 0, and it is equals to minus 1 when we have t less than 0. So this is the definition of modulus t. So what we are going to get here, so if we find out the Fourier transform x omega, then it is or xf, we can also written xf. So it is limit a tends to 0, minus infinity to plus infinity, e raised to the power minus a modulus of t signum t e raised to the power minus j omega t into dt, where omega is equals to 2 pi f. Where omega is equals to 2 pi where omega is equals to 2 pi f. So it is written as limit a tends to 0. We can write it as minus infinity to 0, e raised to the power at, e raised to the power minus j omega t into minus 1 into dt, because signum t is equals to minus 1. And from 0 to infinity, we have e raised to the power minus at into 1 into e raised to the power minus j omega t into dt. So this is x omega. This is x omega. Now we are going to find out. This value of this integral. So it is very simple to compute. And what we are getting here, that limit a tends to 0. We are getting here minus 1 divided by a minus j omega plus 1 divided by a plus j omega. So this is a solution we are getting after solving the integral. Now if we just solve this, then what we will get here, we will get minus a minus j omega plus a minus j omega divided by a minus j omega, a plus j omega. So it is limit a tends to 0. This will cancel out, so it will become minus 2j omega divided by a square plus omega square. Now if we apply the limit a tends to 0, then what we will get? We will get 1 divided by omega 1 divided by omega multiplied by 2 multiplied by minus 2j. So what we will get here, 2 divided by j omega, and it is nothing but 1 divided by j pi f. So x omega or xf is equals to 1 divided by j pi f. So Fourier transform of signum t. So Fourier transform of signum t is equals to 1 divided by j pi f. 1 divided by j pi f. Now using this relation we can find out the Fourier transform of ut, that is unit step. So next problem is find out the Fourier transform of the unit impulse signal. Find out the Fourier transform of unit impulse signal ut. So find out Fourier transform of ut. So let us solve this problem. So what is the relation between signum t and ut? So if we see that signum t, then signum t is equals to +1 when we have t greater than 0. So signum t is equals to +1 when we have t greater than or equal to 0. It is -1 when we have t less than 0. So this is the definition of signum t. Now the relation we can find out the relation between signum t and ut, and we can just write that signum t is equals to 2ut minus 1, because if we carefully observe that, so ut for t greater than 0, ut is equals to 1. So signum t will become 2 into 1 minus 1, so it will become 2 minus 1, that is equals to +1. So for t greater than 0 it will become +1, and for t less than 0 ut is equals to 0, so signum t will equals to -1. So this is -1. So this is signum t. So it can be written as 2ut minus 1, and we have proved that it is equals to 2ut minus 1. So the signum t is equals to 2ut minus 1. Now what we are going to find out the Fourier transform of. So how to find out Fourier transform of ut? So ut can be written as signum t plus 1 divided by 2. So ut is written as signum t plus 1 divided by 2. So what we are finding out here, that Fourier transform of ut is equals to Fourier transform of signum t plus 1 divided by 2, and that is equals to Fourier transform of signum t divided by 2 plus Fourier transform of 1 divided by 2, and that is equals to 1 divided by 2 and Fourier transform of signum t plus 1 by 2 Fourier transform of 1, that is equals to del t. Because del t has Fourier transform 1, then applying the del t property, 1 has Fourier transform of del minus f, that is equals to del f. So it is equals to del f. So it is equals to del f, and the Fourier transform of signum t we have derived in previous question, that it is j pi f plus 1 divided by 2 del f. So the solution is 1 divided by 2 del f plus 1 divided by j 2 pi f. So this is the Fourier transform of ut. So this is the Fourier transform of ut. So Fourier transform of ut is equals to 1 divided by 2 del f plus 1 divided by j 2 pi f. Also we can write this relation in terms of omega. So Fourier transform of ut can also written as pi del omega plus 1 divided by j omega. So this relation, if we write in terms of omega, then instead of f, so it is equals to pi del omega. We have just multiplied by 2 pi here, and this we have written in the form of omega. So it is pi del omega plus 1 divided by j omega. So this is the Fourier transform of ut. This is the Fourier transform of ut. Find out Fourier transform of u minus t. So next question is find out Fourier transform of u minus t. Now if we see the dilation property, then we can say that that is xt has Fourier transform xf, then xat has Fourier transform 1 divided by modulus of a xf by a. Now if we take a is equals to minus 1, so what we will get, x minus 2 minus t, the Fourier transform is x minus f. So if xt has Fourier transform xf, then x minus t has Fourier transform x minus f. Now let xt is equals to ut, so the Fourier transform of this signal xt, that is equals to xf, and it is equals to, the Fourier transform is equals to 1 by 2 del f plus 1 divided by j 2 pi f. Now Fourier transform of x minus t, that is equals to u minus t, is Fourier transform of u minus t is equals to x minus f. So x minus f, instead of f we are going to replace with minus f, and it is equals to j2 pi minus f, and it is, since it is an even function, so it will remain the same, and this 1 divided by minus j will become j 2 pi f. So this is the Fourier. So Fourier transform of u minus t is equals to del f divided by 2 plus j divided by 2 pi f. So Fourier transform of u minus t is equals to del f divided by 2 plus j divided by 2 pi f. Now find out the Fourier transform of t e raised to the power minus at ut. So let xt is equals to t e raised to the power minus at into ut, where a is greater than 0. So find out Fourier transform of ext. Find out Fourier transform of ext. So let us discuss this problem. So that Fourier transform of e raised to the power minus at into ut, all of us know that it is a plus j 2 pi f. So the Fourier transform of e raised to the power minus at into ut is 1 divided by a plus j 2 pi f. So if we just multiply with t e raised to the power minus at into ut, then the Fourier transform will be equals to 1 divided by minus j 2 pi f d by df of 1 divided by a plus j 2 pi f. This is simply the differentiation property we have used. So according to this differentiation property, if we have a signal gt, and if the Fourier transform is gf, then if we multiply it with j2 pi t with this gt, then the Fourier transform will be equals to d by df of gf. Then the Fourier transform will be equals to d by df of gf. So this is the Fourier transform. So we have e raised to the power minus 8 into ut. The Fourier transform is equals to 1 divided by a plus j 2 pi f. Then t e raised to the power minus 8 into ut. The Fourier transform is 1 divided by minus j 2 pi f into d divided by df 1 divided by a plus j 2 pi f. So that is equals to 1 divided by minus j 2 pi f, and it is equals to if we solve this, then what we will get here, we will get that differentiation is equals to minus 1 multiplied by a plus j 2 pi f minus 2 multiplied by 0 plus j 2 pi f. So finally what we will get here, we will get here 1 divided by a plus j 2 pi f whole square. So the solution is the Fourier transform of t e raised to the power minus 80 into ut. The solution is the Fourier transform is 1 divided by a plus j 2 pi f whole square. This is the solution of t. This is the Fourier transform of t e raised to the power minus 80 into ut. That is 1 divided by a plus j 2 pi f whole square. So let us discuss another problem that is very important problem, and we need to find out the Fourier transform of. So find out the Fourier transform of xt is equal to 1 divided by a square plus t square. Let us find out the Fourier transform of this signal. So if we remember that we have already derived that if we have modulus e raised to the power a modulus t, then the Fourier transform of this signal is 2a divided by a square plus omega square. So this is the Fourier transform. Now what we can apply? We can apply the duality property. So what duality property is saying that if gt has Fourier transform g omega, then gt has that omega is replaced by t, had the Fourier transform 2 pi g minus omega. This is the duality property. Now we can apply this property. So what we will find out that 2a divided by a square plus t square, if we replace omega with t, then the Fourier transform of this is 2 pi e raised to the power minus a modulus of minus omega, and that is equals to 2 pi e raised to the power minus a modulus of omega. So this is the answer. Now what we can do that we just divide left hand side and right hand side by 2a. So what we will get? We will get 1 divided by a square plus t square has the Fourier transform is equals to pi divided it is equals to pi divided by a e raised to the power minus a modulus omega. So this is the Fourier transform of, so pi divided by a e raised to the power minus a modulus of omega is the Fourier transform of 1 divided by a square plus t square. So let us solve some problems related to the Fourier transform. So let us solve one problem. If find out the Fourier transform of xt, that is 1. So find out xf. So solution of this is, again we are going to apply the duality property. So according to duality property, if gt has Fourier transform gf, then gt has Fourier transform g minus f. So del t has Fourier transform 1. So if 1, so this is in time domain, so this is in time domain, this is in frequency domain. If this is in time domain, then the Fourier transform is del of minus f, that is equals to del f, because delta function is even function. So I am just going to explain it by figure, drawing the figure. So del t has Fourier transform is equals to 1. So del t is, this is del t, at t is equals to 0, this tends to infinity, so this is del t, and the Fourier transform is 1, means we have a flat line, and this is the Fourier. So if this is xt, then this is xf, so this is xf. Now if we take 1, that is if we take xf is equals to 1, then the inverse Fourier transform. So if we take here we have taken xf is xf as 1, the Fourier transform of del t is 1. So this is in this is in frequency domain. Now if we replace f by t, so if we replace f by t, it means now it is xt, that is equals to 1. So if we draw that, then this is 1 xt, this is xt, this is xt, and that is 1. And if we find out the Fourier transform, then Fourier transform is simply a delta function, present at f is equals to 0, and the amplitude tends to infinity, and the amplitude of this delta function, so this is the amplitude of this delta function at f is equals to 0 will tends to infinity. So we can use this property and find out the Fourier transform of 1. Okay, now again if we have xt is equals to 1, so if we take omega, then the Fourier transform of del omega is equal, the Fourier transform of del t is equals to 1, then 1 has Fourier transform 2 pi into del minus omega, and that is equals to 2 pi del omega. So if we write in terms of omega, then we have to multiply it by 2 pi. So whenever we have del f and del omega, so what is the relation between these? So del omega is basically if we have del f, then it is equals to 2 pi into del f. So here we have the Fourier transform of 1 is del f. If we want to convert into omega, then again we can write 2 pi into del omega. That is also correct in terms of omega. So this is the relation between that f and omega, del f and del omega. Let us solve another problem, that is xt is equals to e raised to the power j omega naught t. So let us do this by using the previous result. So 1 has Fourier transform del f. Now this one is in time domain. If it is multiplied by e raised to the power j omega naught t, then the Fourier transform is del f minus f naught. And what is omega naught? Omega naught is equals to 2 pi f naught. Now if we have another signal, that is xt is equals to e raised to the power minus j omega naught t, again we can apply that. So 1 has Fourier transform del f, then e raised to the power minus j 2 pi f naught t, that is I have written omega naught by 2 pi f naught. The Fourier transform is of course del f plus f naught. We have a very basic signal. What we can do, we can find out the Fourier transform. So the next question is, find out the Fourier transform of signum t by using the delta function. By using the delta function. So let us solve this problem by using the delta function. We can find out the Fourier transform of signum t. So signum t is equal to 2 times ut minus 1. So signum t is equal to 2 times ut minus 1. So this is the relation between signum t and ut. This is the relation between signum t and ut. Now how can we find out that this Fourier transform of signum t by using the delta function? So if we differentiate on both sides, what we will get? We will get d by dt of signum t is equal to d by dt of 2 ut minus 1, that is equal to 2 del t minus 0. So d by dt of signum t is equal to 2 del t. Now taking the Fourier transform on both sides, so Fourier transform of d by dt of signum t is equal to Fourier transform of 2 del t. So it is j 2 pi f Fourier transform of signum t, that is equal to 2 into 1. So Fourier transform of signum t is equal to 1 divided by j pi f. This is the relation we have derived earlier. So this Fourier transform of signum t is equal to 1 divided by j pi f. So we can find out the so let us do another problem. So the problem is using the convolution theorem. Using the convolution theorem, find out the inverse Fourier transform. Find out the inverse Fourier transform of x omega is equal to 1 divided by a plus j omega whole square. So let us do this problem by using the convolution theorem. So as we know that e raised to the power minus 80 ut, the Fourier transform of e raised to the power minus 80 into ut is 1 divided by a plus j omega. So this is the Fourier transform of e raised to the power minus 80 into ut. Now ax omega is equal to 1 plus 1 divided by a plus j omega square. It can be written as this x omega, it can be written as 1 divided by a plus j omega multiplied by a plus j omega. We can write in this way. Now this is if we find out the inverse Fourier transform, then we will find out that so the inverse Fourier transform of this is xt, and the inverse Fourier transform of this is e raised to the power minus 80 into ut convolution with e raised to the power minus 80 into ut. Here we have applied the property that, which property we have applied is that since it is multiplication, so multiplication in frequency domain is equal to convolution in the time domain. So what is happening here, if we have x1t convolution with x2t, then if we find out the Fourier transform, then it is equal to x1f multiplied by x2f. So here we have multiplication in time domain, and if we find out Fourier transform of this, then it is convolution in frequency domain. So these two signals are basically, we see that first signal is 1 divided by a plus j to omega. The second signal is also the same signal. So these two signals are multiplied in f domain. So if we find out the inverse Fourier transform, then it means that these two signals are basically convolved in time domain. So xt is equals to e raised to the power minus 80 into ut, convolution with e raised to the power minus 80 into ut. And what is the definition of convolution? So let us write the definition. So if x1t has convolution with x2t, then it is written as minus infinity to plus infinity x1 tau x2 t minus tau d tau. So we can apply this property, and what we will get? So what we will get, minus infinity. So xt is equals to minus infinity to plus infinity e raised to the power minus a tau u tau e raised to the power minus a t minus tau u t minus tau d tau. Now what we can see here, it is equals to minus infinity to plus infinity e raised to the power minus a tau e raised to the power minus a t e raised to the power plus a tau u t minus tau d tau. This is the relation. Now what we can see here, this will cancel out. So this will cancel out, e raised to the power minus a tau and e raised to the power minus a tau, this will cancel out. What we will get here, it is minus infinity plus infinity e raised to the power minus 80, we can put outside, and we have u tau ut minus tau d tau. So we need to find out what is u tau and ut minus tau. So let us define u tau. So u tau is equals to 1 for tau greater than 0, greater than or equal to 0, it is 0 for tau less than 0. ut minus tau is equals to 1 for t minus tau greater than 0, it means you have t greater than tau, means tau less than t, and it is equals to 0 for tau greater than t. For tau greater than t. So so basically this u tau is defined only between 0 to t. So this term is only, so u tau ut minus tau will be equals to 1 when we have tau less than t, and it is equals to 0 otherwise. So we have e raised to the power minus 80 only from 0 to t. Only from 0 to t this term is equals to 1, and all other values it is equals to 0. So it is equals to 1 when we have tau less than t and tau greater than 0. So this is our final answer. So so we can just I am going to summarize. So t e raised to the power minus 80 ut has Fourier transform is equals to 1 divided by a plus j omega whole square. Now let us do another problem. Problem is verify the integration property. Verify the integration property minus infinity to t x tau d tau, that is equals to, if we find out the integration, that is equals to pi x0 del omega plus 1 divided by j omega x omega. Let us verify this property, that is equals to minus infinity to t x tau d tau is equals to pi x0 del omega plus 1 divided by j omega into x omega. So if we can write this xt as, we can write xt as ext convolution with del t. This is the definition. Any arbitrary signal can be write in terms of convolution with del t. So so what we can do, we can, if we integrate on both sides, then in minus infinity to t xt dt is equals to minus infinity to t ext convolution with del t dt. So we have integrated on both sides from minus infinity to t. Now what we can see here, that so minus infinity to t ext dt is equals to, we can separately write it as ext convolution with minus infinity to t del t dt, and that is equals to xt convolution with ut, because ut is minus infinity to t del tau d tau, because ut is minus infinity to t del tau d tau. So this is simply we are writing minus infinity to t ext dt is equals to ext convolution with ut. Now what we can find out, that if we take the Fourier transform on both sides, so Fourier transform of minus infinity to t ext dt, that is equals to Fourier transform of ext convolution with ut, and that we can write it as x omega, that we can write it as x omega Fourier transform of x omega Fourier transform of ut. So we can write in terms of omega or f, whatever we have. So right now I am using omega, and we will see in f also. So because this is convolution, so convolution in time domain is equal to frequency multiplication of frequency domain. So the Fourier transform of xt is x omega, and Fourier transform of ut is, we have written here, so x omega multiplied by Fourier transform of ut. So that is equals to x omega, and that Fourier transform of ut is, we have derived earlier, that is equals to pi del omega, that is equals to pi del omega plus 1 divided by j omega. So that we have, that is equals to pi x omega del omega plus 1 divided by j omega into x omega, and that is equals to Fourier transform of, that is equals to Fourier transform of minus infinity to t ext dt, that is equals to Fourier transform of minus infinity to t xt dt, that is equals to pi x omega del omega plus 1 divided by j omega x omega. Now we can apply the property here, that x omega del omega is equals to x0 into del omega. So we can see that the Fourier transform of minus infinity to t xt dt is equals to pi x0 multiplied by del omega plus 1 divided by j omega into x omega. So this is the Fourier transform of, this is the Fourier transform of this signal. Now we can write this in terms of f also. If we just divide by 2 pi, then it will convert into f. So we can use this property and we can find out. So we can use this integration property and find out the Fourier transform of ut. So let us do another problem. So by using the integration property, find out the Fourier transform of ut. Find out the Fourier transform of ut. So we can find we can say that ut is equals to minus infinity to t del tau d tau, and that Fourier transform of del t is equals to 1. The Fourier transform of del t is equals to 1. These two relations we already know. So these two relations we have known. So xt is equals to del t. Let xt is equals to del t, and that x omega is equals to 1 and x0 is equals to 1. That we know, because that if del t, then that Fourier transform of del t is 1. So this 1, so at 0 we have value 1. So x0 is also equals to 1. So this xt, so xt is equals to del t and x omega is equals to 1. For this Fourier transform is 1 for del t. Now what we can see that we have seen that ut is equals to minus infinity to t del tau d tau, and that we can write it as pi x0 del omega plus 1 divided by j omega. So that is equals to pi, because x0 is 1, pi del omega plus 1 divided by j omega. So that is equals to the Fourier transform. That is equals to the Fourier transform of ut. So the ut has Fourier transform is equals to pi del omega. It is equals to pi del omega plus 1 divided by j omega. So ut is equals to minus infinity to t del tau d tau, and the Fourier transform is pi del omega plus 1 divided by j omega by using the integration property, by using the integration property. Let us do another problem. Find out the Fourier transform of xt is equals to e raised to the power minus a t square, where a is greater than 0. So find out the Fourier transform of ext, that is a omega. So x omega is equals to minus infinity to plus infinity xt e raised to the power minus j omega t into dt. This is the definition of Fourier transform. So if we just divide with respect to omega, then dx omega divided by d omega, it is equals to minus infinity to plus infinity. So here xt is e raised to the power minus at square. So it is equals to minus infinity to plus infinity e raised to the power minus at square e raised to the power minus j omega t into dt. So if we differentiate, what we will get, So we will get, so let us combine these two exponential here before differentiation. So it is minus infinity to plus infinity e raised to the power minus a plus j omega t into dt. A t square plus j omega into so this is we have combined these two exponentials. Now if we differentiate with respect to omega, so what we will get? Just differentiation of this will gives us we can further write it as minus jt minus infinity to plus infinity e raised to the power j omega t plus at square dt. So basically this dx omega divided by d omega, we can solve this relation. By using the integration by part. So it is t e raised to the power minus at square multiplied by e raised to the power minus j omega t into dt. So we can do the integration by part. We can solve this by using the integration by part. So what is that integration by part? So it is u v dx is equals to u integration of v dx minus integration of u dash integration of v dx and whole this bracket, whole bracket, then we have integration of dx. Now we can use this formula. This is the integration by part formula here, and what we will get here, dx omega divided by d omega. So here we have u we have taken as u is equals to t e raised to the power minus at square. So here you have two signals, two functions. We are going to use this integration by parts. So what we can take, u is equals to e raised to the power minus j omega t, and we can take as t e raised to the power minus a t square. Now let us solve this. So first we have to write this u, that is e raised to the power minus j omega t. Then we have integration from minus infinity to plus infinity t e raised to the power minus a t square, and this is multiplied by j minus j. So and it is from minus infinity to plus infinity, then minus we have minus infinity to plus infinity, then we have differentiation of u, that is simply u dash, that is u dash is basically differentiation of u du by dx. So the differentiation is e raised to the power minus j omega t. So the differentiation is with respect to t here, So what we are getting here, it is minus j omega, and we have integration, and from minus infinity to plus infinity t e raised to the power minus at square dt, and whole bracket, the bracket is closed, and dt. So we are going to solve this. Integral. So what is the value of this integral? That is minus infinity to plus infinity t e raised to the power minus a t square dt, and that is equals to minus 1 divided by 2a e raised to the power minus a t square. Please check this relation. Please check this relation. So again we have to apply the integration by part, and we will find out that minus infinity to plus infinity t e raised to the power minus a t square dt is equals to minus 1 divided by 2a e raised to the power minus a t square. So again I putting all these values, here. So what we will get? So what we will get here? We will get the final value of dx omega divided by d omega. The value we are getting is minus j omega divided by 2a minus infinity to plus infinity e raised to the power minus a t square e raised to the power minus j omega t into dt, and that is nothing but it is equals to, so if we just carefully see that, then what we will get, that this dx omega divided by d omega is equals to j minus omega divided by 2a ex omega. So this is simply a differential equation. So this is simply a differential equation. So solving this differential equation, differential equation, for x omega, we obtain x omega is equals to a e raised to the power minus omega square divided by 4a. This is the solution for this first order differential equation. So where what is a? So where a is an arbitrary constant, where a is an arbitrary constant value, So our aim is to evaluate the value of a. So evaluation of constant a. So let us evaluate this constant a. So to evaluate a, we proceed as follows. So setting omega equals to 0, in equation x omega a e raised to the power minus a omega square divided by 2a. So setting omega equals to 0, we get x0, that is equals to a, and it is equals to minus infinity to plus infinity e raised to the power minus a t square dt, and that is equals to 2 times 0 to infinity e raised to the power minus a t square dt, and that is equals to under root pi divided by a. By using the definition of gamma function, it is under root pi divided by a. So what we are getting finally, we are going to substitute the value of a. So substituting the value of a, we get, so what we get, x omega is equals to under root pi by a e raised to the power minus omega square divided by 4a. So what we are getting finally, so hence we get e raised to the power minus at square for t greater than 0. That Fourier transform is under root pi by a e raised to the power minus omega square divided by 4a. So this is our time domain, this is our xt, this is our xt, and this is our x omega. So this is in time domain, this is in frequency domain. So this is xt, this is x omega, this is xt, and this is x omega. Both have Gaussian shapes. Both have Gaussian shapes. So this is the amplitude under root pi by a. So please note that. So it is seen that. So it is seen that Fourier transform of Gaussian pulse signal, Fourier transform of Gaussian pulse signal is also Gaussian pulse, is also Gaussian pulse in the frequency domain, is also Gaussian pulse in the frequency domain. So the Fourier transform of Gaussian pulse is, so Gaussian pulse in time domain Fourier transform is also Gaussian. Fourier transform is also Gaussian. So that important conclusion is that exponential minus pi t square has the Fourier transform exponential minus pi f square. This is very important result. This is very important result we are getting. In f, if we are just writing in f, then exponential minus pi t square will give the Fourier transform exponential minus pi f square. So Gaussian pulse in time domain is also, the Fourier transform is also Gaussian,